program synthesis. So we're going to start with the first paper by Nadia Polikova and Ilya Sergey. I want to point out that this is a distinguished paper, so be excited about it. It will be great. Also, please keep in mind you can ask questions via Slido, so make use of that.
Thank you, Robert, for the introduction. Wow, no pressure. All right, so that's the work with my amazing co-author Nadia Polikarpova. It's about program synthesis. And this is the work that had been enabled by a very simple and very powerful idea that we all know in the programming language area. And this is the idea of Curry-Howard correspondence. That tells us that type theories are proof systems. And hence, types are propositions, and programs are proofs. In other words, doing the proof search is the same as doing program synthesis. What is the type theory for programs with pointers? Well, that is indeed separation logic. So if I could summarize in one short sentence what this work is about, well, that is about doing program synthesis using separation logic. And this is pretty much everything you need to know about this work. And since I have 17 more minutes to fill in this talk, I'm now going to show some examples of how exactly we do that. So the hello world of the synthesis of programs with pointers is the program that swaps two pointers. So the pointers are the two different memory locations. Let's call them X and Y. And they point to some untyped values. Let's call them A and B. And this is what we are going to do. We start from writing the specification for this function and give it a telling name. So, and to say what the procedure does without telling how it does it, we can write a precondition saying that initially X points to A and Y points to B, and then the postcondition that tells that eventually X should be point to B and Y should point to A. And let me point to your attention that this is the connective that makes everything possible. This is what's known as separating conjunction, or pronounced separately. And this is the biggest enabling element of separation logic, as introduced by Hearn, Reynolds, and Young. So this is our goal. And we start from our goal having no program. But if we consider a very restrictive language with no allocation, no deallocation, and no access to any values besides what's already in the specification, then it turns out there is not very many things that we can do. And one thing we can start from is substantiating these values that are in the heap, but that are not the parameters of the function. So naturally, the first thing to do would be to read, let's say, from X. And that gives us a real program level variable, which is going to be called A2. And what you can see that the goal has changed. So now the pre and post conditions of the whole to be generated are different. So we can continue this process and do the same for B. And now we have the pre and post conditions that have no logical variables, only program level variables. And now we can start doing something interesting. Next thing we notice is that X points to A2 and at the beginning and X points to B2 at the end. So the natural thing to match this impedance is to write B2 to X. Well, and I guess you know what's going to happen next. I'm going to do the same thing for Y. Curiously, if we look at the residual goal that we have here, we'll see that the pre and post condition and the pre and post conditions, they are even syntactically the same. So clearly the pre and post precondition entails the post condition. And that means there is nothing left for us to do here. In other words, we can conclude that the synthesis is over and we have the program that satisfies the specification. So this is precisely what the programmers, I presume, will do, except they probably would be more efficient and use just one temporary variable that they assign. But here we are. Now the goal is to generalize this pattern. And to generalize it, let's recall how do we do reasoning with symbolic heaps in the pre and post condition. And the standard form of reasoning about symbolic heaps is to consider the program entailment of this form. Heap entailment. And this formula says that any heap that satisfies the predicate P also satisfies Q. So there's a lot of work published on the subject of proving the entailment. I'm not going to focus too much on it there. So when the programs come to the play, we get what's we know as Floyd-Howard triples. And the semantics of the triple is as follows. If the initial state satisfies P, then after the program C terminates, the final state satisfies Q. So the simple idea that we try to implement is to blend these two things together into this new logical connective, which we are going to call the transforming entailment. And the transforming entailment is the goal and the proof of this goal is a program. So the semantics of that is as follows. If this thing holds, if there exists a program C, so there exists a proof term, such that for any initial state satisfying P, C, after it terminates, will transform into a state satisfying Q. And this is what we have developed in this work. So obviously there are some natural implications. For example, P entails Q implies that P transforms to Q. And the proof term for that you can think of is simply the program that skips. Also, we can write more complicated things, such as from x points to some a, eventually x points to 42. And here's the proof term for this program. So we are going to write these derivations in the following way, saying that P transforms to Q via program C. So to enable the proof search in this logic, we had to slightly polish the traditional presentation separation logic, and what has been the result we call the synthetic separation logic, in which this is the main judgment. So in fact, we have to slightly generalize it to keep track of the program level variables and distinguish it from the logical variables. And the goal is this triple of gamma, P, and Q. The ghost variables are the logical variables that appear in the pre and post conditions, and the existential variables are such that only appear in the post condition. So it turns out when you have this formulation, it's very easy to come up with the basic rules of the logic. For example, if you have a precondition, which is an empty heap, and the post condition, which is an empty heap, you can imagine what kind of program satisfies that transformation. So there is nothing else here to do. Something more interesting, now we have a pointer x that points to some a, and a is the logical variable, it's a ghost. So the natural thing to do here is to read from this thing. And what is the result here is the program that starts from reading from x and also synthesizes the rest of the program in a modified Go, where a is now replaced by the program level variable. That's precisely what we did in our example. What about this one? Here we have x points to something in the beginning, and x points to some concrete expression E such that all its variables are actually instantiated and they are program level variables. Well, clearly we can write E to x, and that will advance our goal. Not necessarily in the right direction, but that's certain progress. Finally, this is something that you can recognize as the key rule of separation logic, which is known as frame. Saying that if we can synthesize the program that works in a small footprint and transforms P to Q, we can equally use this program in a larger footprint where the pre and post conditions are enlarged with the same heap R. So now even if we take these 4 basic rules of the logic, that's already enough to synthesize the swap. And this is how the derivation would look like. So we start from our basic goal, and then we apply the rule for reading once and again. And then this enables applying rules for writing. So we write to x, and now we see that what x points to in the beginning and the end is the same. So we can just frame it out. And now we are only left with the footprint that has to do with y. So the next thing to do is to write to y and apply the frame rule again. And eventually we are left with something very simple, which is the empty heap. And this is where we finish. But now if we read the proof derivation bottom up as it would be in a sort of continuation passing style, we can also read off the synthesized program. And this is how we get the swap following just the logical derivation. So obviously, you can have only so much fun deriving programs that swap pointers, and eventually we had to move to something more interesting, for which we extended the pre and post conditions with the pure parts that constrained the values that appear in the heap. So this is nothing unusual. Separation logic has it too. And the bread and butter of separation logic is reasoning about recursive data structures, such as a linked list or the trees. And that is done by means of inductive predicates and the recursion. So this is a familiar picture that all of you remember from the class on algorithms. This is a heap-based linked list, which has a head and has a tail. And separation logic gives this beautiful and concise algebraic data type-like looking inductive predicate that describes the shape of the heap that implements a linked list. So it has an empty part, which is the case when x is a null pointer, and it has a non-empty part, which says that the elements of the list are such that there is an initial element, there is a rest, and there is a pointer to the tail, and then the whole structure repeats itself recursively. So it turns out that once we have the inductive predicate defined, we are having fantastic power to synthesize recursive programs, because the inductive predicate effectively gives us a recursion scheme for synthesizing the recursive programs. So the hello world of recursive programs that manipulate with linked list would be the list deallocation with a nicely pleasant specification that has list in the precondition and an empty heap in the postcondition. To generate this recursive program, we start from what it is, but you see this annotation with 0 and 1, and this is the only tricky bit we had to introduce to ensure that the program that we have, they are not vacuously correct. So we also ensure that the programs, they actually terminate, and we do it by means of some very simple syntactic stratification tracking the unfoldings of the predicates. But that's technicality, so let's see in fact what is happening here. We start by observing that the predicate has two clauses. So this is effectively a disjunction, which we can dispatch by means of an if statement, looking at the guards and seeing if the head pointer is the null or not. And we just replicate the pre and post condition. And now we are starting to inline the spatial part of the inductive predicate. In the first case, it gives us the fact that the list is empty. So we have empty here, and clearly there is nothing left for us to do. So congratulations, we have just synthesized a half of the program. So the second half is slightly more interesting because here we actually have the proper recursion, but we also have a number of pointers with the ghost variable. So y doesn't make an appearance in the parameters, so clearly we can read from this x plus 1, and this is what we do using the read rule. And this is how we synthesize the next part of the program, advancing our goal. Now we focus on this block. So this is actually an array of two elements for which we have this indicator, and this is quite common notation for representing contiguous chunks of symbolic heaps in many tools such as Verifast. And this serves as a trigger that informs that actually we can apply the deallocation command. And there is a rule for that in the logic which I didn't show, but trust me, it is there. So we deallocate this part that has been just completed, and this is what we are left with. And this is where the crucial part happens. So by having these annotations with 0, 1, essentially the levels of unfolding, and knowing that our predicate is productive in the sense that we always need to chip off some part of the heap before the recursion kicks in, we can now apply the recursive/inductive hypothesis, knowing that the symbolic heap, symbolic footprint has decreased, and hence the program has the termination measure. And by applying that, we receive the postcondition of the recursive hypothesis, which is amp. And this brings us to the familiar goal, which has an empty heap in the precondition and an empty heap in the postcondition. So clearly there is nothing left to do. And now if we step back and take a look at the big picture, we will see that we have precisely synthesized the destructor. So destructors are very pleasant to synthesize, but obviously we can also synthesize something that is constructive and that produces the data structure at the end. But this, and all these examples are in the paper. So to give you the big picture, this is what the logic looks like, and even though it might be a little bit intimidating, this is the entire logic. And it's quite declarative, so you can implement it in your favorite tool, and it gives you the strategy for the proof search. So what exactly are the formal guarantees that come with this synthesis? Well, it turns out that we get the benefits both of program verification and program synthesis. And the first natural theorem that we had to prove, that if we have synthesized the program by means of following the proof search in this derivation, then this program also satisfies its pre and post condition in a traditional Hoare-style sense. Second, and this was actually quite important, we prove a stronger statement, which is actually a total correctness of the synthesized program. So the programs had been synthesized. If the program has been synthesized using this, this proof search, it also terminates, and that is what has been ensured by this stratification when unfolding the recursion. So having this proof system, we have the synthesis algorithm pretty much for free, because that is essentially a proof search algorithm, and the proof goals are the specifications, and the algorithm obviously has some backtracking. It's implemented using CPS, and it just iterates through the fixed set of the rules that we have seen 2 slides before. It has some branching, because some rules have alternatives, and most of the non-determinism in branching happens because of the need to unify the pre and post conditions. And the interesting part that along the program, it also emits the complete proof tree. So it turns out the vanilla algorithm works well, but it's also not very efficient. And that, in this case, we had to take advantage of the fact that we are in a proof theory. So we can apply nice techniques such as focusing and consider some rules are invertible. And also we could structure the search in phases and apply what's called the early failure rules. As interesting as it is, I'm not sure I have time for that, but all the details are in the paper. So this is a nice and rosy picture, and you might wonder what are the limitations. And obviously, there is no particular magic here, and all things that we can synthesize, they typically fall into the following classes. First of all, the specifications need to be inductive if you want to synthesize a recursive program. Second, the recursion schemes, they are defined by inductive predicates, meaning that we cannot have, at least for now, things such as quicksort. And, okay, one more. So we also synthesize using unfoldings up to the fixed depth. And naturally, since there is some reasoning with pure fragment is involved, the expressivity of the synthesis is limited by expressivity of the decision procedures that we use for the pure logic. So we use Pressburger arithmetic, set theory, basically everything that Z3 has to offer. But the interaction between the pure and the spatial synthesizer is quite minimal. So in fact, it's actually quite easy to plug more theories and synthesize more programs with more expressive pure parts. So a couple of words about implementation. So this tool has been implemented in Scala. It's runnable. The tool is called Suslik, which actually is an acronym for synthesis using separation logic, German style. And it's available on GitHub, and also it's available as a web tool to try on. Since the counter shows that I still have 2.5 minutes to fill, let me do a super quick demo to show you that indeed the tool works and you can synthesize something interesting using it. So I hope you guys can see that. And for example, this is what the specification for swap looks like. So it's exactly how it was on the slides. And so the reason why it starts kind of slowly, because JVM takes some time to take off, but the synthesis is very fast. And this is just the resulting program, but also you can have the trace that corresponds to the proof derivation. So we didn't quite check the proof derivation itself, but you can see this is how the rules have been applied, and that's precisely what we have done for swap. So since I have not that much time, I'm going to show only one program, which is my favorite, and this is the program that copies the list into another list. So the specification is quite curious. We don't have return statements, so we pass the return pointer and the initial list with a set of elements S. What we want is the very same list, but also its twin brother that starts from Y, and the return pointer now points to that. So if we ask the tool to synthesize that, something interesting will come out. So this is the resulting program. And it's maybe not very pleasant to read, but there are a couple of peculiarities. The first peculiarity is this reassignment. So I always thought that implementing heap abduction is something that happens to other people. But unfortunately, we had to implement it too. So the reason why we need an abduction here is that the precondition actually requires for the recursive call the return pointer to point to the head of this tail. And this is not something we have at this moment. So what we need to do is to abduce a program that would make an extra write to this pointer. And this is why we need the abduction. So that's the first peculiarity about this program. The second peculiarity about this program is, in fact, it doesn't copy the list going like that, as you would expect. Instead, it goes like that, swapping the pointers at every movement. And we were quite baffled to see such a pattern, but then, well, that's perfectly normal. It's just not the kind of program that the human would write. But here we start some interesting questions about what is actually proof relevance and what is the proof irrelevance in this setting. So that was the demo. We have many, many more programs to show. The specification to code ratio is quite pleasant in favor of specifications. The times are reasonably fast. And the only tool which is out there that does something similar, although works not in the proof search setting, but in inductive setting by means of starting from the sketch, that's the tool by Shokan Q and Armando Solar Lezama. And we were quite happy to see that for most of the cases, except for the most SMT heavy, we are order of magnitude faster. To take away, so the message is very simple. And probably most of you know that separation logic is a proof system for heap-manipulating programs. That means that we can turn it into a synthesis tool, which we did and implemented in a form of the Suslik framework. And that's all I've got. Thank you.
Thank you. So let's start with some questions from Sri.do. If you have an inductive predicate where there is not like a clear disjunction, like x equals 0 and x is unequal to 0, then the synthesizer would have difficulty building an if expression for it
Yes. Okay. So the question is, how do we handle inductive predicates with overlapping guards? And the question is that there is nothing specific here. So the guards are treated in the order they appeared in the inductive predicate, and the ifs are just emitted. So a chained sequence of if-elses is emitted to match each guard in the order they appear. And the last guard, that's what is in the last else. So obviously there is some assumption that these things are complete and mutually exclusive, but well, this is not enforced.
Okay, can we have a question from the audience? Okay, I see someone in front.
Very nice talk. So for the fragment you support, can you have a completeness theorem? Because you showed the soundness one.
So the question is, do we have a completeness theorem? The answer is no, and it's very interesting, and this is what we are working on right now.
Right.
Okay. Could you already come to the front and I ask another question from Sridhar do? In the list 3 example, why did it not also synthesize a load for the X maps to V?
Why didn't synthesize the load? Okay, so that's actually a very good question. So how come that we ended up with this program without taking false turns? Oh, well, obviously I have cut all the false routes that could have been taken. And one of these routes could have been a reading from the pointers and trying to do something with it. But then eventually the synthesis would hit the unsatisfiable goal and realize that this is not what should be done. So the nice road to take would be to implement free. And the phased search that I've mentioned is precisely about arranging the rules in the order that would maximize the chance to hit the right derivation faster. But yes, so that route could have been taken, it just wouldn't satisfy the
Okay,
the
one last question, and could the next speaker set up in the meantime?
Can you talk more about the termination?
Okay, so we have not proven. Okay, so the synthesized programs do terminate. Whether the synthesis algorithm terminates, we have not proved exactly. So we do have something that looks like a matrix, and for all practical examples, it has terminated. But so the only problem that could have been is the interference between the unfolding rules in the case of recursive predicates. And we were quite careful in using these tag annotations to make sure that it progresses and eventually it terminates. But again, so the termination of the algorithm is not proven.
So does it rely on the fact that the data structures are acyclic, you have lists and trees only?
Yes, so one important assumption is that we have only well-founded predicates that make the program, the search terminate.
Okay, all right. Thank you very much, Ilya, and thank you very much for the questions. Let's move on to the next talk. So the next talk will again be about synthesis, because we're in the synthesis session, and it will be by Kenson, Jacob, and Percy. So please go ahead.